clear this for you guys. So for a second, because most of what's happening in an engine is either a mixing problem. We're trying to combine two substances that won't necessarily combine on their own, fuel and air. We're trying to combine them such that we have all the atoms spaced the same from one another in an ideal case in a cylinder in a highly turbulent environment, that is not laminar. It's not like we can squirt this in and wait for it to, it's not like perfume in a room. It's not diffusion. You're not going to just squirt it in the corner and then after 10 hours, the whole room has the perfume across the whole room. That's what we were taught in school. It's called diffusion. It'll happen naturally. The fuel that goes into an engine has a very short time period to be dispersed into the volume that you're trying to create a homogeneous region. Port injection for a long time was the accepted de facto way, and you would use some amount of heat to squirt the fuel onto a hot intake valve, and it would kind of sizzle and disperse. Some of it would be left on the valve, some would be left on the wall, and the speed in which the air that flowed into the engine would carry that fuel in. It would be somewhat dispersed as it went through, and it would mix, and you would ignite it, and you would have some level of homogeneity within that mixture. DFI has brought it a whole nother level, much more like a diesel engine, where we can squirt it in there not at 70 or 90 PSI. We can squirt it in there at 2000 PSI. And because of that, we can have really, really small holes in the injector, which make incredibly small droplets, which disperse in a very wide area. Or even better, which Charles, I know he's wanting to go here, you can squirt it at a piston of a certain design, make it bounce off the piston and come back into a more preferred
that's a good word.
Design or homogeneity, which is not necessarily homogeneous, which is more concentrated in one area of the cylinder and very less concentrated in other areas of the cylinder. So that's a more advanced topic. We'll come to that later. But the gist is you can generate horsepower and you can control things by how you inject the fuel into the cylinder. Is that fair?
Yep.
Okay. Our producer just put in something that's wrong. MS-109 burns hotter and faster is what Justin just presented, and I will take the bait. Thank you. It is, and he did that on purpose. Yes. Thank you very much, because he knows better. We've talked about this. MS-109, let's talk about octane for a second. Octane is a hydrocarbon with 8 carbons in it. Anytime you see an ane and a Latin numbered number, Latin
octane, benzene, cetane.
So Benz is he just threw a curveball. He's trying to fuck y'all up. So octane, heptane, nonane, et cetera, are the linear constructs for hydrocarbons. That's octane is 8, heptane would be 7, nonane is 9, decane would be 10, dodecane is another number. Keeps going and going. And gasoline is a general construct for all of them. The octane rating of a fuel is an indicator of how fast it will burn. A lower octane number will burn faster. A higher octane number will burn slower. There are other additives you can put into the gasoline that will allow it to burn slower or faster. A cyclic molecule like benzene or others that are like benzene are unique in their properties for how they burn. Benzene and other cyclic hydrocarbons will control their environs in a stronger state than linear hydrocarbons. How's that for an explanation? You can put a little bit of benzene in there and it will have a large effect on how linear hydrocarbons are influenced. Mm-hmm. This is the whole chemistry of your neighbor kind of thing. And this is some advanced quantum physics shit. We're not going to get into that. How electrons
eventually
are shared.
We'll do the what happens when you put acetone in your gas tank.
Ooh, yeah, that's a fun one. So MS-109 is a race fuel designed by VP Fuels, and it has an enormity of carcinogens in it that are not good to breathe, but are very good for combustion and are incredibly good at staving off what's called knock or pre-ignition, or a misfire isn't related to those things, but a lot of you will understand the word a little better. The firing off or the ignition cycle of lighting off the fuel is controlled better with MS-109, or is more predictable.
Yes.
It's more predictable based off of when you ignite it and the homogeneity of the mixture. It's more tolerant of inhomogeneous mixtures and burning slowly. Thank you, Justin. This is a fucking rabbit hole, but it's an important rabbit hole, I suppose.
I need a bigger shovel.
Jesus, this is going to be a 4-hour YouTube. Good luck cutting this thing down.
So something that's important. Everyone's been there. What happens when you actually push the gas pedal on a car? Why does the engine rev up? Okay, so I'm not going there, but at some point somebody didn't know that, and then you get it.
Rabbit hole.
Well,
but yeah.
What is knock? And then what is combustion? What's ignition? What's the correct process?
Yep.
Why do you need, other than everyone says, oh, we need higher octane because you have higher pressure and make more power. Well,
yep.
What's the
why do you need those things?
Best word ever.
Yep.
Why?
Yep.
So if you take and there's knock, detonation, pre-ignition,
yep.
whatever. Knock,
they're related, but they are not the same.
Yeah, they're similar. They cause similar damage. They look differently when you take an engine apart. So if you have your fuel in your chamber and the spark plug,
igniting the fuel
voltage
mixture,
across the gap, ignite the fuel mixture, and you have the flame front propagating across, not just across the piston.
And I'm the one that's drinking whiskey. Yeah. He's drinking coffee. So
English, my third language.
Exactly.
I don't even know the first two. Math, numbers, maybe.
Yeah, exactly.
So as the flame front is propagating outward, and I'm using outward because this is our application.
Yeah,
I'm not dealing with old school. So
the thing's in the middle, and it's going to flow out this way.
As it flows outward,
yep.
as you're increasing a burn.
Yep.
The pressure in the cylinder is increasing.
Yep.
As the pressure increases, it goes from the center high pressure out, high pressure to low pressure.
Yep.
And it is the pressure wave and the burn
is like a sphere. It's going to go out in all directions.
Out. So now you're taking this, in theory, homogeneous mixture, and you're pushing it.
Yep.
And now the pressure is increasing across the bore faster than the burn is spreading.
Yeah. Yes. So because the pressure wave leads the combustion.
Think of anyone who's looked at a video of a bomb going off or an explosion or something. And
bullet exiting a gun, or even better, a nuclear explosion is better for this.
I won't recreate that one. Not today.
Thank you. Appreciate that.
But just a bomb, missile, something, and you get the shock wave.
Yep.
We have the shock wave in the cylinder.
Oh, that's a whole nother thing to talk about. But yeah.
But you get this wave, and it compresses all the air and fuel together even more so.
Yep.
Pre-ignition and detonation and knock is when you have a combustion, or the process, the fuel burns / explodes at the wrong time.
Correct.
From the wrong source.
Imagine pressing on your pedal when it's still rising.
Correct. So you're essentially, this pressure wave increases and it compresses everything so tight that it heats up enough and it causes the fuel to ignite on its own, not from the main controlled source.
Yep.
There's that pre-ignition, and then you also have pre-ignition and knock. They're similar, they're different. I'm going to get into some other time. But that control is not good. That's when you get pistons that have damage on the outer side of it.
Yep. ring lands that are broken in a turbo engine.
If you had an engine that had a perfectly homogeneous mixture in it, and you had pre-ignition on that point as that wave spread, you wouldn't have a little mark. You would have one big mark on the inside.
Exactly.
So that all those little marks when you see on a piston from pre-ignition,
which most people haven't pulled an engine apart that's been broken.
Most haven't. They just throw it out in something else. But that's from poor atomization or mixture, whichever.
Poor mixing.
With that is when you okay, we need higher octane. That's the noise generally you hear when you tip into the gas and you get the ball bearing dropping in a can thing with it.
Popcorn and that kind of thing.
And the knock control goes off on it. So that's you need higher octane. That's why they 87, 89, 92, or California it's like
91
50.
Horseshit gas. May as well be freaking oil you're boring
MS-109 has it's 105 octane rating, I believe. And some people say, well, it's got more octane than 105. Well, somebody's classified it and engineered it as that. But it has a higher resistance to pre-ignition and detonation. And we've, on the naturally aspirated stuff we do here, we've yet to find the limit of it.
That shit's the way we can test for MBT. We can literally pour that in there, and like on the Cup car, Cup car, street car, whatever, you can run as much. Charles has been able to on our dyno, and this is really cool to see, that you can keep increasing the ignition advance. And this is a little bit more of an advanced topic, and we'll come to this. So this is the pedal analogy. As ideally, the most ideal time to press on the pedal as it's coming up past top dead center, which would be 12 o'clock, is like 3 to 5 degrees past top dead center. And pushing on it then gives you the longest amount of time to apply force, and it also gives you the longest. So back to our
there's actually an equation for figuring that out on everything.
Because the RPM goes up, then
the rod stroke length and the piston crush height and all that, the sinusoidal sinusoidal equation for that, which is it's not difficult, but when to use it in this
construct, right? So he's gotten to the point where he's been able to increase the ignition timing, i.e. when the flame expands and when it's at its peak and pushing on the piston, that he can see the torque begin to drop, which means that the peak pressure is actually hitting the piston as it's starting to come up to the very top, and it's reducing the torque. That's not a thing you want to keep doing, because eventually you'll start to flatten out bearings and or worse, you'll bend rods,
lift the heads,
all that stuff. If it's a turbocharged car and it's making 10,000 horsepower, things just fucking explode at that point. Kaboom. But it's cool to be able to find that point, because then you know exactly how much efficiency and how much horsepower you're making at that RPM and in those constructs. So you know, okay, this is the most it can make because we just sneaked past the ignition constraints or the flame speed constraints of the engine. Now we're looking at how much air is coming in and exiting only.
And if you have enough math and data numbers, you can actually calculate this pretty close. Maybe not perfectly, because you're also assuming that the air fuel in the chamber is perfect. So you kind of have a range that you have to know roughly, but I've done a few ignition maps that were within 2 to 3 degrees of correct.
Which is crazy.
Just based off of changing from
multiple thousand RPM.
Which you can find for the manufacturer online, all the deals, and then calculate flame speed of the burn based on the chemical, E10, E15, whatever, and then go from that to MS-109, which they hide some of this stuff.
For sure.
And then do the difference between it, and then do a map, and then there we go, and then make some adjustments. So it's not just like no one ever wants to just go in there with a laptop and just say add
all the ignition, go, boom.
That's when shit blows up.
It's when you break shit. All right, that's enough on fueling. We kind of covered ignition a little bit. Coil, spark plug, dwell. We're going to talk this about a second. So a spark plug is the thing that has this is Jesus Christ.
Think of for all of you that have your illegal gas stoves in California.
Yes.
It is the piece when you go to turn the knob and click, click,
Tick, 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 tick. It's the ticky thing.
It's the same.
Yeah,
Not identical,
it's the thing that's making the voltage drop across a gap that creates the lightning bolt. That's the lightning bolt.
It's like a household taser.
Yeah, it's a taser. Tick, 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 tick. So that
boom.
That's that. The coil is the thing that is providing the energy for that spark to exist. So it has to build up a large amount of voltage so that spark has energy. The dwell is the amount of time the coil has to charge so that it can disperse that energy. Hotter coils, cooler coils, bigger coils, we're not going to touch that for now. We're going to leave that the fuck alone. Same thing with spark plugs, hotter spark plugs, cooler spark plugs. We're going to leave that alone. That's more about over time, how much carbon builds up on a spark plug based off of the amount of the fuel mixture that it's running and the amount of heat that is going through the spark plug as its use. That's a fucking rabbit hole. We're going to leave that alone. Ignition advance. We kind of already talked about that. Ignition advance is getting after how early, based off of the fuel that I'm using and how much area I'm trying to encompass, I need to light off that mixture because it doesn't happen instantaneously. It takes time. So you have to light it off as the engine is spinning faster and faster. You may have to light it off earlier and earlier by degree. Degree is crank degree as the crankshaft is spinning, like we told earlier. Maybe it's 30 degrees before top dead center so that I start to light that mixture as the piston's really coming up quick. And I want it just to be at its peak pressure as the piston's just on the other side of top dead center so it can push it down.
Go ahead. Just zoom in here.
Yep. The very top of the cylinder.
The piston is at the bottom.
Yep.
And it is rotating through the motion this way. This is what it would look like up and then down the rod swinging here. Well, as the piston is approaching top dead center, the rod is rotating.
Yep.
And then you don't want to, if you just took the piston and rod and had it at top dead center, TDC is
that was peak pressure.
Peak pressure, and if it stayed here, you would have a pressurized increase that will go from on a piston of this size. This is about 10 inches of surface area.
Yep.
Well, a combustion process might meet and exceed 3,000 psi.
Times
3,000 pounds per square inches times 10 inches. That's 30,000 pounds of actual force.
Yep.
Now, it just sitting here statically,
that's
going to break or bend something, which happens, which is when guys lift heads, they bend connecting rods. You see the connecting rod all squiggled and stuff. Bearings, your bearing contact point is two concentric circles that when you increase the pressure, they go from being concentric to coincident, which means they intersect at a line.
Coincident, good word.
Right?
Yeah, that's a good word.
At a line, two-dimensional line,
yep.
which is 10,000 pounds of force on one line, which flattens bearings really quick.
Mm-hmm.
So you want to have the piston moving up and start the burn early because it's a burn, it takes time.
Yep.
And then you
this
want
piston's moving really fucking fast at that point.
Yeah. Up, and it's going to change rotation.
Yep.
And then you want the peak cylinder pressure to be at the right point, and this changes based on rod length, stroke length,
yep.
piston diameter,
RPM,
bits, piston
yep.
crown design
yep.
matters, RPM, so that the piston is at the right leverage point to have the most force to push on the connecting rod on
yep.
the crankshaft. Same thing in your bike. If you're riding a bicycle and you push on the pedal right at the top, you kind of pushes you
off of it,
and that's when it's trying to blow the engine apart. So it's critical. Engine companies who design engines for a living, all manufacturers, Porsche, McLaren, Cosworth, whatever.
Yep.
They don't guess on this. You can calculate it all.
Yeah.
Now, programs, math, everything's on computers nowadays. But it's that
and they give themselves some bandwidth. They don't run it right on the ragged edge of optimum power.
And there's the emission side of it. There's also the octane side. So when you have an engine, these engines generally are not tuned for 91 octane Cali gas.
They deal with it, but they're not tuned for it. They're generally not happy.
So we've got to adjust stuff. We're not going there with it. But if you go from an engine tuned on 98 octane,
yep.
the burn happens, it's calculated and just set up for the certain rate of burn. At a certain time, you go from 98 to 110 octane to get the racetrack. This is different reasons for this. That burn's going to happen slower, so you might be able to retune the engine, adjust the timing like a lot of other companies do to account for that. We do that as well.
This is a good time to talk about it. So, what about my tuner telling me that I have a stage 2 tune? What did he do? How did he find horsepower in an already, quote, optimized engine from Porsche?
Same way you find Bitcoin, just get a computer and start mining it, right?
Fucking A, right?
Yeah.
So generally what a tuner is going to do in that regard is they're going to tell you have to run octane boost or you have to run 100 octane or something like that, and they're going to limit the amount of adaptation that the engine has for ignition advance. They're going to potentially limit the knock sensitivity of the engine so that it doesn't intervene and reduce your ignition advance. And in essence, in some cases, he's going to make the engine closer to blowing up than Porsche did. Because Porsche is going to give you a really wide berth because they don't want to be replacing engines under warranty.
This engine, this 3.8 981 GT4, sold I don't know how many hundreds of D4 kits, intake, everything, a lot of them in California. This engine here, actual numbers, a stock car running at Laguna Seca in the 90 degrees, you have to remove 8 to 12 degrees of ignition advance to get it to not run on the knock sensors all day long. And usually it'll go into limp mode because it's running so much ignition advance. When you take an engine that makes that much power and you now want your car to be faster, you start modifying it. Well, now you have more cylinder pressure. So now the engine has more stress, more on the knock system. It's trying to detonate more. Now there's other thermal variants here we can get to later by changing exhaust components, but that's one thing. Everyone says, hey, I want my car to be quicker, when just taking that engine from 91 octane gas to 100, even just 100 octane on unleaded 110 will keep the car from running on the knock sensors, detonating. It's running on the knock sensors just means it's every cycle, it's got detonation, pre-ignition, and the knock sensors sense this, and it is adjusting the ignition timing so it doesn't...
It's pulling it back, trying to keep it from knocking, and then after a certain number of cycles, we'll try and add the ignition back in, and then it'll see that it knocks again, then it'll pull it back out.
And most Porsches eventually, after so many cycles, it'll actually just knock it down,
yank it all back out.
Say, okay, I'm always pulling 12 degrees, and it just caps it, and just always there. Higher octane in this case will allow you to run the full potential of the engine. Where it's supposed to be running, especially with intake air temp, where hot air can help create more detonation or quicker in a poorer fueled engine. Maybe not in anything how Porsche designs it. They're
getting into the 201 subjects,
octane doesn't mean you need to do all the tunes. A lot of companies do that. They just crank the timing up. A 981 GT4 engine in that bone stock, because I've tuned a few of these for guys. My car goes into limp mode after 20 minutes at Laguna in summer.
It's like, let me fix that.
Just go in, just stock some quick adjustments with it where it's not just pulling timing and it's running happier. We'll usually make more power and run the whole day. Just from letting it run normal, not just, hey, you have to run race gas in it all the time. Race gas does have, I say race gas, higher octane fuel does have advantages to where you're just allowing the engine to run normal all the time as it was intended, especially in more extreme conditions.
It's not trying to manage what's going on, it's just able to run. It's not running off all of the fancy sensors and control strategies to enable it to survive. Now it's just running.
There's a little more depth past 201 maybe, but in a turbo, 911 turbo, 997.2 turbo, 991.1.2, GT2 RS, their thermal management is pretty advanced.
It's pretty sophisticated.
They're trying to keep the engine, number one, car has to pass emissions. Everything out the tailpipe has to be clean. If your engine melts from track use, but it's burning clean for the environment, that's okay. That's what they're not going to get sued for that. Engine melted because of incorrect use.
That's just a warranty thing.
Correct. Hopefully.
That's not a $1 billion lawsuit.
Correct. Hopefully that's Dieselgate all over again here.
Right.
So if you have a GT2 RS, I'll say a Turbo S, street car, touring car, not a track car, and you go run on track all day long in California with 91 octane gas and an engine that makes 620, 650 horsepower at 20 pounds of boost.
Yep.
It'll run that all day long. It is designed to make that much power on 98 or 100 octane.
And the thermal constraints of the engine are designed to be able to pull all that out, all that energy out, and keep the engine running right.
And what happens when you, it's knocking, we're going to pull 10 degrees of ignition out, which on a turbo engine, that much power, it might only be running 5 or 6 degrees of ignition timing.
Yep.
So now you're making, when you retard the timing from whatever the number A, the delta, 10 degrees. The burn is starting 10 degrees later.
Yep.
And what happens is you're limiting your cylinder pressure. The piston goes up and it burns and it comes down. You're limiting that volume. As you go from piston at top dead center to down, say, rod angle 10 degrees, the piston moves down, I'm going to say a quarter inch, your volume's doubled.
Sure.
So if you had 3,000 PSI at TDC and you move the piston down and your volume's doubled, you're half the pressure. So they're limiting the peak pressure.
Yep. PV equals nRT, y'all. That's the ideal gas law. Those two things are related linearly.
That's
You're welcome.
Remember that. That'll be on the quiz next time.
Yeah, that's next time.
So as you retard all this ignition, you have the burn happening later. Eventually piston goes down, piston comes up, or piston goes down, exhaust valve's open, you have this later burn happening. All the exhaust gas coming out of the cylinder is now burning later than it was intended to.
Yep.
You have
which is now hotter.
It's hotter.
Yep.
Well, it's the same amount of heat at a later point in the stage.
Yeah.
So instead of more heat being able to be used to expand
consumed in the cylinder to push the cylinder down,
it's going out the exhaust. Now you have more heat going out the exhaust.
Yep.
Exhaust valves
get
have
hotter.
more heat to deal with exhaust port. Turbo engine,
turbos do, right?
And you will, if you do this on the dyno, which we've dyno everything in the world here, get everything red hot. GT4, 91 GT4, we have so many videos. Exhaust flowing red hot after 1 or 2 pulls from pressure differential restriction.
Doesn't do a good job of getting it has
you can't get the
it's not as efficient. Yes.
So you get these turbo engines on this 91 octane, the exhaust starts glowing really hot. Well, they actually have they use oxygen sensors, the resistance in them to gauge the temperature.
Yep. So a version of an EGT sensor, but using an oxygen sensor.
All the new turbo thermal managed ones, they actually have EGT sensors in them and OPF engines that are monitored as well. I believe we don't have those here, the monitored ones. So the exhaust gas temp gets hot enough to measure, not just modeled.
Yeah.
And they start saying, okay, this is too hot, we got to pull it down. And they'll start cutting the boost, or you can adjust cam timing, you can change injection.
Releasing cylinder pressure.
You will be reducing, and I've seen one log from a guy, same guy in Cali, who buys everything, tracks everything stock, and sends me this log.
Yep.
And it's just horrible. It's just
the car's just pissed.
The car's just not happy. He's doing 4 hours of track at Laguna. It was like 113 degree exterior temp.
Right.
His intake air temp was over 200 degrees, if I remember right.
Jesus Christ.
And
that's a park the car level.
Correct.
Don't do this.
So he wanted to mod his car. He wanted us to build an exhaust for his car. And I was like, well, hold on, what's the goal? Well, I want my car to go faster. And this was like a Turbo S executive.
You wanted to go faster on Venus?
So I told him,
come on.
I was like, take your car, go to the pump.
Yeah.
Put some 100 octane or 110 in it.
Right.
But clear all the adaptation codes first.
Yeah.
So he didn't want to do that because it's $20 a gallon for fuel. I'm like, well, you want to spend $50,000 on mods.
Right.
Race gas is a mod. Tires, slicks is a mod.
Right.
You know, all
Aero is a mod. All these other things are a mod.
He sent the log back with the car. Right. He said he went like 17 or 18 miles an hour faster down the street.
Yeah, car's fucking happy.
It was happy. It was quiet just from changing octane with it. But the engine wasn't going to limp mode. Everything wasn't glowing red hot when you parked the car.
Yeah.
So
there's a whole lot to unpack from that.
Yeah.
There's some 201 level stuff, and we'll get to that. As you retard ignition, exhaust gas temperatures increase because more of the energy that you're trying to consume with pushing a piston down is now released by the exhaust valve opening early and letting all of that out into the exhaust tract. So you've now made the engine more thermally inefficient by trying to fix your desire for running more ignition timing on shitty gas, and then the engine is trying to fix it and not blow itself up, and it's putting a whole bunch of extra energy into the exhaust stream that is now wasted. So that's essentially what Charles was just saying. If you allow the engine to run the way it was designed to, with an octane that burns slower so that it can capitalize on that cylinder pressure when it needs to, it won't pop the safety valve, so to speak, and open the exhaust valve and eject all of this energy out of the cylinder too early. That's enough on ignition.